Our Chapter 10 practice problems look at drawing Lewis structures and finding molecular shapes. So first we're going to look at Lewis structures of ionic compounds. So our example is Al2O3. So we can use Lewis structures to explain what happens in ionic bonding as well as covalent bonding. So to start, we're going to take our aluminum and we're going to write the dot structure of the element. So if we look at our periodic table, so aluminum is 1, 2, 3. It's in group 3 here. So it has 3 valence electrons. So we'll write Al 1, 2, 3. And the next aluminum, same thing, 1, 2, 3 valence electrons. Now let's look at our oxygen. So on our periodic table, oxygen is right here. It's in group 1, 2, 3, 4, 5, 6. So we have 6 valence electrons for oxygen. Okay. So we'll have our O, 1, 2, 3, 4, 5, 6. O, 1, 2, 3, 4, 5, 6. And our third one, O, 1, 2, 3, 4, 5, 6. So covalent and molecular bonding occurs to get the most stable configuration of electrons, or that noble gas configuration. So our metals will lose electrons to achieve the previous noble gas. So for aluminum, it's going to lose these outer 3 electrons to have the same configuration as neon. So these are going to turn into neon by losing electrons, and our oxygens are going to gain electrons to also become neon. Okay, so electrons lost and gained, they have to have somewhere to go. So we're going to lose electrons, so that one's going to be lost and paired there. This one would be lost and paired here. Okay, so this oxygen gains 2 to have the same configuration of neon, or to have 8. So that has its 8 electrons, but this aluminum still has an extra one. So this extra electron is going to go to this next oxygen atom. Okay, so now aluminum has lost all 3, and again it has the same configuration as neon. This oxygen has gained 1, but again this guy still is unpaired, so we'll gain another one here. So now this oxygen has its octet. We still have these 2 extra electrons for aluminum, so they will go here and they will pair here. Now everyone has the octet. So we want to show what this looks like in kind of a Lewis diagram. We'll have our Al3+, so it has lost all of its little sort of electron dots here, so we don't show any in the structure. So we have 2 aluminum 3+, and we have 1, 2, 3 oxygens. So here we'll have our oxygen with all of the dots with that -2 charge. Oxygen with all of the dots with its -2 charge, and then that final one, that oxygen with all of the dots and the -2 charge. So we showed the valence electrons here that were lost for our oxygen to go into the shell of the oxygen to form our 5 ions, all of which have that noble gas configuration of neon. So this is what happens with ionic compounds when we look at electrons being gained and lost. Okay, so for molecules a little bit different. So our next example is to look at the molecule of sulfate, or not sulfate, excuse me, sulfur dioxide. So number 2, we're going to look at SO2. Okay, so we want to draw the Lewis structure for SO2. Okay, so this, a little bit different. We have to sum up our valence electrons and then draw our structures. Let me get some pens here. This should probably work. Okay, so let's start by summing up our valence electrons. So sulfur and oxygen are both in group 6 in the periodic table. So sulfur has 6 valence electrons, and each oxygen also has 6. So for our total, we get 6 plus 2 times 6. Essentially, we have 3 times 6, or 18 electrons. So when we make our Lewis structure, we have 18 electrons to use exactly to build our structure. Okay, so when doing this, generally speaking, our element farthest to the left goes in our center. Since these are both in the same column, we're going to choose the least electronegative to put in the center, which will be sulfur. Plus, sort of the fun fact that oxygens don't really form covalent bonds to other oxygens. Okay, so we'll put our sulfur in the middle and an oxygen on each side. Okay, so the most common type of bond in nature is a single bond. So we're going to start by attaching single bonds. So when we do that, we have 1, 2, 3, 4 electrons. So I'm going to keep a tally over here. We had 18. We used 4 in bonding, which leaves us 14 left. Okay, so now we're going to distribute the lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we distribute our lone pairs on our SO2, and we see that after using all 14, so we used all of those here, we have 0 electrons left. Okay, so let's look at all of our atoms. So we circle our sulfur here. Inside there we have 2, 4, 6, 8 valence electrons. This oxygen over here, if I circle it, 2, 4, 6, 8 valence electrons. And then my other oxygen over here on this side, we have 2, 4, 6. So only 6 electrons in the valence shell of this oxygen. So when this happens, when you're building a Lewis structure, this tells you that you don't have only single bonds in your structure. So I'm going to take these lone pair from sulfur, and I'm going to swing them over. So if I take this lone pair and turn it into a bonding pair, they're still in this circle here with sulfur. I am just moving them over into the shared region. So when I do that, I get my oxygen now with a double bond to this sulfur with 1 lone pair, and then this oxygen on this side still keeping its 1, 2, 3 set. So I just turned a non-bonding pair into a bonding, so it still stays in the valence shell of sulfur, but is now also counting for this oxygen, which is short. So we get the oxygen, a double bond on one side, and a single bond on the other. So this would be our Lewis structure for SO2. Okay, so the rest of the problems here, we're going to refer back to this Lewis structure to answer 3 through 6. Okay, so number 3, what is the electron geometry of SO2? So we're going to circle our central atom, which is sulfur, and we're going to count our electron groups. So we have 1, 2, 3. So we have 3 electron groups. So 3 electron groups. So if we look on our chart for how many electron groups and what shape we get, this gives us a tetrahedral shape. So if I were to draw that, I would have my sulfur, I would have my lone pair, I would have my double bond to oxygen, and I would have my single bond to oxygen. So if I were to, again, draw this, putting all of my electron groups in there, I have the 1, 2, 3, the tetrahedral shape with 120-degree bond angles approximately. So approximately 120 degrees, and this is trigonal planar. So we have a nice trigonal planar geometry here. So this is the electron geometry. So electron geometry. Okay, so the next question asks, what is the molecular geometry? So I'm going to take this shape, I'm going to draw it exactly the same, but I'm going to leave this lone pair off. So I'll have my S, my O, and my O. Okay, everything about it the same, but I'm going to leave this off. So now I've taken the lone pair out, and I'm just looking at the bonds. So I still have about 120 degrees here, and this shape is called bent. Okay, so when we have the 1, 2, 3 electron groups where one of them is a lone pair, we get the bent shape. So is SO2 polar or nonpolar? So we're going to look at the symmetry. So when you're deciding if something is polar or nonpolar, you always want to go back and look at the electron geometry. For something to be nonpolar, every single position in the electron geometry has to be the same. So in order for this to be nonpolar, this, and this all have to be the same thing. That will make it symmetric, and that will make it nonpolar. So if we look in position 1, we have an oxygen. Position 2, we have an oxygen. But in this third position, we have a lone pair. So these three are not the same. So we do have an asymmetric shape, which is going to make this polar. So if we were to look, oxygen is more electronegative. It's pulling electrons away from sulfur this way and this way. And there's nothing up here to sort of counter that pull to make it equal and opposite. So because we have an asymmetric shape here, this is going to be polar. So it's polar and it's asymmetric. So this would be polar. Okay, so our last question here asked us, show any resonance structures for SO2. Okay, so if we look back to our Lewis structure here, we have our sulfur double bond to oxygen on this side and a single bond to oxygen on this side. So the way I originally did my Lewis structure up here, I kind of started with this oxygen and worked my way here, which left this one short. But I very easily could have started with this oxygen to give it the octet with the 3 lone pair and had my double bond on this side. They both would have been good Lewis structures and they both would have been identical. So that's what it means with resonance. When you have a choice in the way you choose which side gets your double bond or which atom gets your double bond. So if we look down here, if we take our original Lewis structure, our O, double bond to sulfur, single bond to oxygen. So this is our first Lewis structure we did. So we can show that these electrons are in motion and these lone pair can travel and be over here on this oxygen, and this double bond can swing over. So for this resonance structure here, I'm going to swing this double bond over. So now I'm going to have a single bond on this side and the double bond is now on this side. So when I do that, this one of the lone pair also has to swing over. So now we have 3 lone pair on this one. That lone pair on sulfur stays, and we get the 2 lone pair now on our double bond. So this and this are both Lewis structures that would represent SO2, and so we call these resonance structures.